Okay, hello everybody. First of all, great song choice. I did consider dancing on stage, but I thought I'd save you all the sight of that. Hope everyone's having a great afternoon. My name is Daniel Lenton, and I'm the founder of Ivy, where we're on a mission to unify all machine learning frameworks. So, first of all, we all know that machine learning has advanced tremendously over the past few years, but very few of us really know what's going on under the hood. We don't know about quite how messy and fragmented the machine learning stack really is, and today I'm going to be diving deep into this mess to then explain how, in my view, we can start to work towards fixing it. So I'll be going through the fragmented ML stack and how to fix it. So, firstly, at the top of the stack, we have the myriad of incompatible frameworks. So these are all high-level APIs which the end user can make use of. We then look one level lower than this, and we have another myriad of incompatible compiler infrastructure. So these are basically what are used to compile the code into efficient representations to deploy on hardware. We then go one level lower still, and we then have a myriad of incompatible hardware, which is actually where the ones and zeros are run, and it's where you can then train and deploy your models. Now, if we zoom out a little bit, we can see that the entire machine learning stack looks a little bit like a server stack. We have the frameworks on the top, we have the compiler infrastructure in the middle, and we have the hardware on the bottom. Now, what you'll notice about this is that not all of the components are connected. They are sparsely connected so that everything doesn't connect to everything else. And another thing to point out here is that whenever doing any kind of machine learning, whether it be training or deploying, the entire machine learning stack is essential. Your framework needs to go down into some compiler infrastructure representation that then needs to go down some hardware. This is necessary to train or deploy or do anything. So yes, it's needed to train, it's needed to deploy to your end users. So let's now say that you have a model and you've trained it and things are working, and now you're ready to deploy to your users. Now, of course, every single framework has some root down, otherwise it wouldn't work at all. So it does create some compiler infrastructure as an intermediate representation, which then does go down to the hardware where it's run. But crucially, you only ever have access to a subset of everything else that's out there. So you don't connect to all of the compiler infrastructure, you don't connect to all of the hardware, and therefore you don't know when you're deploying your machine learning model whether you're really having the optimal solution for what you care about. Maybe you care about accuracy or runtime performance or memory efficiency or whatever it might be. There's something that's really important for your application, and there is a combination of hardware and infrastructure that works for it, and you might not have access to it because you only have access to a subset of this stack, basically. And this is a problem because, of course, then you end up wasting time and money with a suboptimal solution deployed to tens of thousands of users in a manner that could be costing you, many millions more than it needs to be. So this is kind of going down the stack. Let's go one level up the stack. So there are several high-level tools which have been built on top, which make the lives of ML engineers much, much easier. The problem is that all of these, again, are left with the problem of trying to keep up with all of the frameworks below. And this is a lot of engineering effort that's required in an ongoing manner. To take a few examples, so I presume some people are familiar with Hugging Face. They have an amazing repository called Transformers, which has to some extent become the open source model hub of machine learning. But they re-implement all of their models in TensorFlow, PyTorch, JAX. This is a huge duplication of effort and a lot of engineering overhead. There's RLlib, which is a repository as part of Ray, which is an open source project by Anyscale. They have a completely separate TensorFlow folder and a PyTorch folder. Again, complete duplication of effort. And then there's also DGL, which has the deep graphics library, which has separate backends for each framework. And I could go on. Basically, a lot of engineering effort is spent trying to make sure these things work with everything below the stack. And this prevents the creators of these tools from really focusing on what they do best, and they're left bogged down with the stack. Now, it would be a slight exaggeration to say that this fragmentation causes the entire stack to spontaneously explode. But nonetheless, it is not sustainable, and this is a problem. So I know what you might be thinking. You might be thinking, is this really a problem? Isn't everybody just using PyTorch nowadays? There's some point to that, but I take a controversial, perhaps particularly nowadays, opinion, which is that machine learning is still more than just LLMs. When you look at numeric computation on the whole, we have things like scikit-learn, pandas, and NumPy used massively in finance and business analytics. We have Julia, used massively for running high-performance physics simulations at NASA and CERN, for example. TensorFlow remains the go-to framework for running models in deployment. In enterprises, it also has superior bindings to edge and mobile devices, specifically via TF Lite. MATLAB, for example, is used by millions of engineers all over the world in aeronautics and automotive, for example. We then have, of course, PyTorch in research, but even there is more going on. Of course, DeepMind remain one of the most innovative AI companies in the world. They implement everything in JAX. There is increasingly a shift towards Chinese native frameworks like Paddle and Mindspore in Chinese universities. And only last week, an entire new programming language was announced, Mojo by Modular, which is headed by Chris Lattner, who's very well known in the compiler space. What this language offers and potentially opens up is the ability for low-level compiler programming directly in Python. And this potentially could undermine the likes of PyTorch and TensorFlow, which operate on a model whereby they have these pre-compiled kernels in C++. And actually, if you can do all of this directly in Python, you might not even need a dedicated framework. The language might be sufficient with some gradient computation. All of this to say, it's not clear what the landscape will look like in 2 years, let alone 5 years, with so much innovation going on. And it is our belief that all of these incompatible tools should be unified such that they're all interoperable and all of the hardware and infrastructure is accessible to all of them, basically. So another thing you might be thinking is, this sounds kind of cool. It might just be a nice research project, but is this really of commercial significance? Well, 18 billion is the average aggregate revenue lost from not having access to models in a timely manner. 13 billion is spent on converting ML code, and 48 billion is spent on ML R&D. So combined, this demonstrates that there is a big problem. There's a lot of value to be created and a lot of money which is spent inefficiently that would not need to be spent if there was a more unified stack. So we've taken a very high-level approach of the stack. I'll now zoom in a little bit more on a slightly more granular level. So first of all, at the top, we have what I see as API standards. QuantSight's Array API standard is a good example of this, where it's not even got an implementation. It's just a template for what the user-facing API should look like. We then have many amazing efforts to enable the writing of framework-agnostic code. What Ivy adds to this, as I'll explain with a few examples, is the ability to automatically convert between frameworks as well as write agnostic code. We then have the fragmented frameworks below. We have graph traces and so on, which are also fragmented. We then get another layer of unification again, where there's been a lot of great work trying to enable hardware-agnostic intermediate representations that are usable across all hardware vendors. And there's things like Onyx, and of course LLVM, MLIR, etc., OpenXLA, TVM, so on. But again, we have this competing standard emerge a bit here. And then at the bottom, we have the vendor-specific, so hardware vendor-specific APIs, compilers, and assembly languages, and so on, where we have fragmentation again. So given that there's all these really good efforts to unify things, why is the stack still such a mess? Well, the answer is complicated, but to simplify things, in my view, I think it can be summarized with these 3 points. First of all, you can't expect everyone involved in ML to suddenly build around your new standard. Best case scenario, many people will adopt it, but several still won't. And if other competing standards then arise or exist, then the fragmentation problem will persist, and we'll have something like this XCKD. So can we take a different approach? So our thinking is that in order to try to improve the situation, we should proactively bind to everything else which is out there, with no need for external efforts, no need for people to come to the standard, nor a need for consensus. So what we're doing is proactively connecting to everything that's out there so that our efforts are aligned with all of these other efforts. We're not trying to compete with standards, we're trying to connect with them so that everybody can be part of this holistic solution. Another thing is that I would say you should use existing standards, don't create new ones. So we are adhering to the Array API standard by Quantsite, which is the standard agreed upon by TensorFlow, PyTorch, NumPy, and kind of NumFocus and so on, so that the industry standard is what we're building around. We're not creating a new one. Also building something that's totally complementary, so no need for any end users to jump ship to a new thing. It should just seamlessly work in the existing stack with no friction. Only requires one line of code, so taking that a step further. And finally, we're building on a high-level mathematical intermediate representation, which is not specific to compilers or anything else, provided that the notion of linear algebra and matrices remain relevant to machine learning, our intermediate unifying representation remains relevant. And I think unless we see fully asynchronous bio-inspired intelligence emerging soon, then this will remain the case. And I don't think we see that for several decades at least. So finally, I'll just leave a few examples of how it looks and how we're going about trying to unify the stack. So the first thing that Ivy enables is for users to build universally. So let's say you want to build a library and you want everyone to use this as easily as possible. Well, if you write your vision library in this case, so line 3, import Ivy vision, if you write your library in Ivy, the functions of this library, we have line 15, this coordinate to voxel grid function. These functions are instantly integratable with all of the existing frameworks. So in this case, it's a TensorFlow Keras model, but it could easily be PyTorch or JAX or anything else. The next thing is the ability to experiment effortlessly. So Cornea is an amazing computer vision library built on top of PyTorch. Unfortunately, it's not accessible to TensorFlow, but with Ivy, with one line of code, it now is. And you can use Cornea entirely in your TensorFlow project. And again, we're really focusing on simplifying the user experience, bringing it to them so that with one line of code, everything just works for them. And finally, it can be the case with a model. Let's say DeepMind release another amazing cutting-edge piece of research. It gets into Nature, and you want to try out this architecture in your project. But your project and your trainer and your data loader are all in PyTorch. Well, again, with Ivy, this is not a problem. With one line of code on line 8, you can get this Haiku model from DeepMind, get it into a PyTorch representation, plug it into your model, and things just work seamlessly. So again, one line of code, super simple user experience, and connecting everything together. Finally, we're also working on the ability to deploy models efficiently so that if you have certain criteria, whether it be runtime efficiency, memory efficiency, cost, whatever you want to optimize, we can look at all the compiler infrastructure and the hardware and find the optimal combination for your needs. So overall, by adopting these principles of being totally complementary, proactively binding to everything that's out there, and bringing the experience directly to the end user, we're pushing for a new era of machine learning where all frameworks, infrastructure, and hardware are totally interoperable once and for all. Thank you very much for listening.